divided this by 12, and I got 6. I divided this by 1, and I got 12. I'm a little nervous about that, but let's assume it's fine. I divided this by 16, I got 1. I'm gonna bail on that. I'm gonna tell you this compound is C6H12O.
Mixed together.
So if we quickly calculate an IHD in support of this, I'm gonna take the number of carbons times 2 plus 2 minus the number of hydrogens divided by 2, and I'm gonna get 1.
That makes sense.
Maybe some of you just saw this was CnH2n and knew there was a single double bond.
Yes.
A singular double bond.
One for one.
One double bond.
That's one.
Can we get our data booklets?
What?
That's a booklet?
Can we get the data booklets?
No, don't get your data booklets that have vital information that you need to answer these questions. No. You need to be in the dark.
She was
It used to be the first module, but I think it was the first module in your 11th grade year.
This is question 15.
This is question 15.
Group data.
I'll make sure it's there. If you put it into your search bar, chemistry data booklet, someone, underlined with highlighter. It wasn't me. We can check the molar mass of this. So we're gonna take 6 times 12 is 72, 84, and 16 more is 100. So when I see the peak at 100, I become sure that that's not the empirical formula, but in fact it's the molecular formula. I also see a peak at 71. That's a loss of 29. That's a loss of either a CHO or an ethyl. And so I could have C5H12, H11. Took me twice to do the subtraction, but I think I got it right. I tried to subtract C, H, and O. And I could also lose an ethyl. That would give me C4H7O. I'm not sure which of those is best. The other point that's discussed is the 29, and that's going to be the presence of an ethyl or the presence of a CHO. There's nothing in my data booklet that would support a loss of 71. So in addition to counting down from the parent peak, I can count up from 0 and take the fragment lost as the fragment found. So this has a lot of narrow action in the 3000s, so that would support it having a CH bond and no OH bond. And it has a very strong absorbance at 1750, which would support the presence of a carbonyl. So I'm gonna write down for myself that the data around 3000 tells me there's no OH, and the data at 1750 tells me there is a CO. Questions that can be asked are both flavors. So they can say, hey, Amarachi, what is the peak at 1750? Or they can say, hey, what does the lack of a broad absorption around 3200 mean?
Lack of it?
Yes, there is not a big fat peak. That means there's not an OH.
And we won't have our data booklet for multiple choice.
You do not have your data booklet for multiple choice, but you should not worry about it. You should know about the broad OH.
Okay.
But beyond that, you shouldn't worry.
So no broad means no OH.
Yes. And do you see that it's not broad because this is made of a sum of a bunch of little thin peaks?
Yeah.
Okay. I don't know. That is like the grossest NMR ever. Hot mess. So I find that relatively hard to interpret, and I'm really grateful that they gave me some data below because the data is just really hard to see. So you can see that there are 4 types of hydrogen, and their relative numbers are 6, 4, 1, and 1. That's consistent with the 12 hydrogens we think are in this molecule. And when I see a 6, what I need to have is 2 methyl groups that are the same. And so if I take 2 methyl groups and attach them to the same carbon, those 6 hydrogens are now equivalent to each other. And I need these 6 hydrogens to be split as a triplet. Well, that would mean this. And that's not good because I'm missing big chunks of my molecule. So I'm just trying to show you my thought process. When I see 6, my first inclination is to take 2 methyls and attach it to a carbon, and then look how it's split and attach the right number of hydrogens. And this clearly can't be the right answer. So when I say I want 2 methyls bound to the same carbon, it's because that's an easy way, but what I really need are 2 methyls that are symmetric. And so maybe it would be possible to do this, 2 methyls, and I'm going to draw myself, I would do this in my head, like a little mirror plane. Just trying to remind myself I need them to be the same. I need them to be symmetric. Now each of these guys is part of a triplet, so it must be next to 2 neighbors. And so now I have, again, this is symmetric, so these 6 are behaving the same way, they'll be split as a triplet. And then these 4, it's fantastic that there's a 4 here, need to be complex. And complex typically means that you have different types of hydrogen on both sides of you. I wish I knew what this looked like. C6H12O. So if I were to do a carbon here, and a carbon here, I don't feel like I have it. It's not obvious to me why this isn't a triplet. And the answer is because it's also split by this H, because it's 1, 2, 3 bonds away. It just didn't look that way the way I drew it. So that's my fault, just missing that H. So I wanted to emphasize the symmetry because that's how I got this 6 and this 4 group. This hydrogen is going to be split by these 2, as well as by this 1, so it would be described as a multiplet. These 2 hydrogens are going to be split by these 3, as well as this 1. That's why it's described as a multiplet. This singular hydrogen is going to be the aldehyde hydrogen that's on the 2nd page of your NMR data, so it's going to be above the mass spectrum data. So you look at table 27, flip the page, you find the aldehyde is supposed to be between 9.4 and 10, and that is where we found this at 9.6. So that was like a hint that we had an aldehyde. It's pretty easy to see that you can lose an ethyl or a CHO in this molecule, so either of the answers that I wrote down for the mass spectrum should be consistent. So just choose whichever one feels good to you. I don't feel like I made this better.
What does integration trace mean?
The integration trace is when you take this thing that's supposed to be an NMR peak. The way the chart recorder works is it's like gonna measure the integral.
So area.
So the area.
Isn't that
And so when it measures the integral, it actually makes a line that looks like this. So the area is rising, 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 rising much less fast on this half, and then finally not changing. And so here it's changing very slowly, here it's changing very fast. It gets to that point of inflection where it starts changing more slowly. And so this shape that looks a bit like an integral sign is what the integral trace is. It's just a setting on the instrument, and this distance is the intensity of the peak, and in this case we would take that distance as proportional to 6 hydrogens or 4 hydrogens. So it's telling you the number of hydrogens of a type, or the number of hydrogens in a given chemical environment.
So that's how you determine that there were 2 methyl groups that had that same.
because I needed 6 hydrogens of the same type, and I don't know how to do that without 2 methyls. So I wanted them attached to 1 carbon, but to make them a triplet, that seemed like nonsense, so then I just tried to make a symmetric molecule so that they were still equivalent to each other. One more? Do you want like 3 minutes to think about it? I don't know that anyone did 19. Maybe they did. Okay, there's a vote for 16. Are you comfortable with 16 instead of 19 in DC? Okay, I mean, you are our puppet master today.
We never made it. We never
It was
did.
very close.
Were we close?
You just had the ester facing the wrong
No,
way.
yeah, it was just.
And it was right, like,
But
We
why?
had the ends correct. It was kind of
I'm so
Yeah.
confused about that flipping thing.
okay.
Carbon. 44?
Yeah, I gotta take 44 divided by 12. I might be able to do it faster than I can turn on the calculator.
Yeah.
This one actually has CAS, everyone. This is the one that's not allowed on either SAT or ACT, but is allowed if you turn it off on all your other exams. It does computerized algebra, so if you enter the square root of 3, it keeps it as the square root of 3, and it does math with radicals.
Oh my god.
It will plot your slope field, all you geeky kids in that class that have to do slope fields next. I don't understand them at all, it will graph it for you.
Yeah, I don't get slope fields. Slope fields are
It will do that.
Then why do we need to know how to do it?
What?
Slope fields are
Quadratics, still like quadratics.
We're not doing
hydrogen 6.6.
I mean, I understand how to make one, I just don't really understand why I wanna
I
make
didn't know
one.
if I was supposed to round up.
Quite
but
yet.
I did, and I got 30.
Like, it looks like I'm just trying to take a magnet and tell you where the iron filings would be pointing.
Divided by 12.
I haven't quite figured out where in science or economics or whatever that picture is gonna mean something to someone.
Yeah.
Because you guys are doing differential equations and you're doing like, there's a chemistry problem coming up, I saw it. There is rate of growth of bacteria that is Unjay's biology IA, like it's very much like pertaining to
This
science.
is an empirical form.
And I just don't know what the slope field is. Very interested.
I just.
Might have to start coming.
I didn't cheat.
Hey, it told me the answer's 11/3. Great. 24 divided by 16 is 3/2.
Three, 4, 6, 6.
Lord.
Yeah. Ugh. C6H9O2Cl.
This is the one.
Is that what you got?
Yeah. Wait, no.
She said that
I thought
0.75 would be the
we
one.
had, I thought we had an 11 at some
So
point.
1.5 would be 2 moles.
But which is one of this is next to the.
Okay, that's 0.73. 6.66 divided by that.
C6H11. Oh, you
I get 9.
6.66 divided by 0.75.
5921.
5921.
43.96 divided by 12.01. That's 3.66 divided by.
Oh, it's 3. I wrote it wrong.
Yeah.
I got 3 before. I just suck a little bit.
3.66 divided by
Okay, I believe that.
equals like 4.88.
Are you comfortable with it?
6.6.
Yeah.
Yeah, I just,
That one?
like,
It went
I
downhill.
read and wrote 2 different numbers.
Like, it was like a black diamond, like
After
ski
this?
slope after that. Like,
Okay, we're good, we're good.
Those are fun.
No, we're good.
They're terrifying.
Very fun.
A is fine. B was okay. C was where we started talking about.
Okay, we're gonna do great on this, because we're amazing humans.
I don't know, I had issues.
You actively don't want me to start the next unit by all accounts. I tried to divide all of these by 0.75, but when I wrote this one down, I wrote down the wrong number because I'm just like a little bit dumb. You divide through by the smallest one. So this is like really 0.73, my calculator knew that. So this was about 2, and then this is 10/3 divided by 3/4. I don't know. It's 49ths, I don't know. I don't know what I'm doing anymore. What else is wrong? Crystal field theory? I call it crystal field theory because that's my favorite part. It will be chapter 13, it will be transition metal chemistry.
So like that.
From scandium to zinc.
Colors stuff.
Colors. Your IA is due January 6th. The rough draft of your IA is due January 6th. The final draft of your IA is due March 8th.
Can you explain to me why
Break is for regular business.
final draft of
Because you have your math IA coming up, it's due in December. And you have your science IAs, they're due in January.
But we don't have our second feedback yet.
Why are I in our feedback?
I suggested that Andre speak to Ms. Peters, that getting feedback on Wednesday and ask for a final copy on Friday was a challenging place to be, and significant changes were expected. But if you're not expecting significant changes, because your first drafts were so freaking awesome, then just be done with it.
No,
And
she's telling
dance
us
and
in
jig.
class.
Like in class, she'll be like, "Oh, you guys are making mistakes that I told you not to make in class." And I was like, "What?" Oh yeah.
I mean, you either need to speak to the teacher, speak to the IB coordinator, or revel in the fact that there aren't gonna be changes made and submit that.
Have you actually talked to
Yeah,
this
we
morning?
talked to her in the last.
It's just because there are so many IAs.
We just don't understand.
That one's much
the
funnier.
extension available.
Yeah, that
She's like,
was-
no, I can't, it's an IB deadline, and I was like, well, we're gonna have less than a week to make any edits that we need to.
Yeah, I
make,
get joy out of
so we
that.
have to make tremendous edits on our end. She's like, well, if you're editing it right now.
She's just
we're-
relentless, you know?
You should be doing better. But if we submitted it to the best of our abilities, how are we gonna be?
Peer review, maybe?
She hasn't even given us our.
That's right, so I'm suggesting that you say, yo, you haven't given my paper, how am I supposed to turn this around? I have a AAHL
She hates giving
test. She hates what?
Giving extensions. And she's always like.
I hate
"Oh,
giving
I need
extensions too.
I know, but
But the thing is, you give us our stuff back.
exactly, yeah, that's the issue. We didn't get our stuff. I remember last time we had a test.
So talk to Liz Murray, talk to Karen Peters.
Talk to Miss Morgan again.
She's
know.
my first choice, but
We only like to talk to people once in this school.
I appreciate the pain, and I know that with my IA, grading the IA rough draft sucks. It is one of my least favorite parts of this job. It will take me a solid 3 hours to make it through Margaret's, then you look at the list and you're like, 90 hours. When do I have 90 hours to work on this? Never. And so it's like, you know what I'm gonna do? I'm gonna go to bed.
Yep. Yepers.
It's hard. But you are in a position where it's October, and so if you need some time, this is some time you could get back. When we're sitting at everything's due April 10th, and y'all don't know what you're doing on April 8th, there's nothing I can do to relieve that, you gotta submit it. April 10th is the day that they need to be uploaded to IBIS. So April 10th is the drop dead date for every IA. That is not in art. I don't understand art, I apologize for that.
Here's the thing.
It has its own rules.
Do you want us all to wait?
No, because some
Yeah, I know that it has different deadlines, but every normal subject, that stuff has to go to IBIS on April 10th. And so everything is negotiable until April 10th. And so if you need to negotiate, take advantage.
I mean, senior class.
Okay, I see two peaks here, a 136 and a 138. They call this 138 the M+2 peak. That's to remind me that chlorine actually exists as 2 isotopes. So if I didn't royally mess this up, which is still a little bit questionable, these two values, I'm hoping, corresponds to those two compounds, where I have either chlorine 35 or 37. So we're gonna try to do this in our heads, maybe it'll go better, I'm not sure. That's gonna be 60, 69, 36, and 35, so that's 71 and 69, that doesn't seem right.
32, not 36.
Thanks. That's 136, because Amarachi's a rock star. See, 2 times 16 is 32. So that worked out really well. 107 doesn't really mean anything to me. It seems like I can see some little action next to it as well as here, so maybe I still have that chlorine. That would be supported by the fact that I haven't lost a full 35. If I took 136 and subtracted 107, that would be 29. And so I suggest that's gonna be the loss of a CHO or an ethyl.
And we don't have to figure out which one it is on that one, right?
That's right, we don't, and so let's not, because I seem to remember this one was right hard.
Yeah.
I was like reviewing and like,
Yeah, it's
I
actually
see
useful.
myself.
We have a peak at 73. If I take 138 and subtract 73, I have, sorry, 136 and I subtract 73, I get 63. I don't know that number, so I'm gonna sit on it, but I see that 63 is also this choice. Now, if I'm feeling desperate, which I might, one of the things I could do is notice that these two add up to this. So one of these pieces probably has the chlorine, and one of these pieces probably doesn't. And so I could try to add things together to get these values. And so what that might look like is, at most, the 73 piece could have 5 carbons. But it cannot have 5 carbons and 13 hydrogens, because that's more than 2n plus 2. So that's some garbage. So it could have 5 carbons and oxygen. It could have 4 carbons and an oxygen. 4 times 12 is 48. 48 and 16 is 64, so that could be H9O. That is a reasonable number. Those values make some sense to me. If I did C3 and O2, as I do have 2 oxygens, this would be 32. This would be 3 times 12 is 36. That would be 68. That's too many. So this is sort of my best guess for the 73 if it doesn't contain a chlorine. What?
It's 63 and 73, like when you.
And so that means that the other piece would be a C, an O, and a CL. And so that's a working hypothesis. I don't know if that was worth my time. But it's like, I can actually conceive of values that add up to this. Here I still have a choice, so I'm not sure that I want to make it. It would be easy for me to subtract either of those and put a plus sign on it. In the IR, there's not a whole lot to be discerned. It's usually going to be worth only 2 marks. With 2 oxygens, I'm thinking that I probably have either a ester or a carboxylic acid. I'm seeing clear evidence that I do not have a carboxylic acid or an alcohol, because this is narrow peaks. I'm also seeing pretty clear evidence that I have a peak in the 17, so I do have a C double bond O. So I have CH and CO. I do not have a an OH. I would guess that this peak right there, someone labeled it for me, was a C single bond O. It looks a little bit pronounced. It's the only other thing I could imagine them giving me, but I don't think any of you have trouble if there's a star here looking in the data booklet and being like, okay, I'll find something. Maybe it's a CCl. I know that's also in that kind of range. But they didn't star anything, so I'm gonna keep it. peak here at 0 is going to be associated with TMS. It's not part of my compound, so I'm going to ignore it. The other peaks have been sort of blown up for me, and the integration traces have been marked in red. So here at 1.2, I have 3 hydrogens, and it appears to be a triplet. And here at 1.8, I have 3 hydrogens, and it appears to be a doublet. That's the triplet blown up, that's the doublet blown up. And then over here in the 4s, I have 2 hydrogens that appear as a quartet, and I have 1 hydrogen that also appears as a quartet. Margaret, you look very... just to make sure that we haven't done something terrible, I'm going to check my hydrogens. The masses were compelling, but here I see that they've allotted for 9 hydrogens, and I have 9 hydrogens. So I feel good. Remember, I had that mistake early on, so I'm still feeling a little nervous about it. So if you appear as a quartet, it means that you have 3 neighbors. And I have 2 things that appear as a quartet, and I have 2 groups of 3 hydrogen. So it seems to me in this molecule I need to have 3 hydrogens that are next to 1 hydrogen, and I need to have 3 hydrogens that are next to 2 hydrogens. So again, these 3 hydrogens will appear 3 tall as a triplet. These 2 hydrogens will appear 2 tall as a quartet. These 3 hydrogens will appear 3 tall as a doublet. This 1 hydrogen will appear 1 tall as a quartet. So all of this is consistent with the splitting in my picture. What I haven't done yet is incorporated 1 carbon, 1 oxygen, 2 oxygens, and a chlorine. So what I'm thinking about doing is putting a chlorine here. That way we wouldn't expect this to split anymore. And then putting something here that also won't let these 2 groups of hydrogen know about each other. And the discussion that we were having at the close of class is that if I believe this to be a ester, the terminology that I used is that the ester can face in either direction. So the ether oxygen can be on the right side, or the ether oxygen can be on the left side, and still the splittings would be correct in our picture. Again, we accounted for 2 quartets, a doublet, and a triplet with the right intensities. To discriminate between these 2 options, I need to look at the actual shift. And so if you're in table 27, looking at the shifting patterns, I hope that we can tell the difference. So if you look at the entry that says RC double bond OOCH2 and puts these H's in bold, that should appear between 3.7 and 4.8. But if you look at the entry that says CH2, let me write it the right way, ROCOCH2, and puts these H's in bold, you're going to find that the shift is between 2.0 and 2.5. So the first one I wrote down is the 4th entry in your table. Those are hydrogens on the carbonyl side. That's this guy. And then the one that I started with was hydrogens on the ether side. That's the one that's 4 from the bottom. So we have both of these groups in the 4+ range. If I put the molecule in this way, with the carbonyl adjacent to this pair, these two hydrogens would appear between 2 and 2.5. That's not consistent with my spectrum, so I think that I've got to do it this way to account for the fact that these two hydrogens are appearing with a chemical shift around 4. Now you might argue that this hydrogen should also be in that 2 to 2.5 because it's next to the carbonyl side, but you'll notice that this hydrogen is also on a carbon with a halogen, and we know a hydrogen on a carbon with a halogen should appear between 3.5 and 4.4. We're not going to be surprised that it's shifted even more because of the presence of this carbonyl. So I'm going to expect this hydrogen, it's just one of them, to be really quite shifted. So I would expect that one to be the one that's farther away. So this would be a true 3.7 to 4.8, and this is going to be a 3.5 to 4.4 more because of the carbonyl.
I have a question.
This is a quartet because there are 3 neighbors. This is a doublet because there's 1 neighbor. So this is angry.
I'm just
Does it make sense why it has to be that way?
Because of where it is on the graph.
It's the position on the x-axis, exactly. Easy for you, Audrey?
I kind of want to check because I'm trying to do it alone because I don't want to like see how you did it and I'm doing my team so like I'm stuck.
But you don't want me to do it.
Like, I know when you do it, really cool stuff.
Are we doing one more, or are we crystal field theorying?
So how do you know which, just to clarify, which peak on the graph is the RO double one?
the one
The right one?
the left one, right?
So this one, because in our molecule, it's got this as well. The chlorine is gonna really, really shift it, and so that's this peak right here. The left one, as your friends told you. You knew it was only 1 hydrogen tall, so that's why it has to be that one, but I'm trying to explain that the shift is really big, because in addition to having the halogen, which would shift it, because it would suck electron density away, we also have the carbonyl that's gonna suck even more electron density away. So we would expect to look at the halogen 3.5 to 4.4 and find it at a bigger shift.
So if it's not one and it's like past 4, why is it the RC double one OCH? Was that different?
So that is this one, also past 4. So since both sides are past 4, I know that this side has the ether oxygen, or the single bonded O, and this side has the double bonded O plus the halogen. So that's how we got 2 peaks to be over here by 4. If you did it the other way, then this single hydrogen would be super shifted. It has 2 things that are pulling on it really hard, so it'd be in the 5 to 6 region, I would suspect. But these 2 hydrogens would be next to the carbonyl side, and they would appear around 2.5. And we don't have anything around 2.5. So that's how I could tell that it had to face the other way. So with it facing this way, I would expect peaks at 2.5 and 5 or 6. With it facing this way, I expect both sets of peaks around 4.5.
Wait, what is it that's pulling on the?
So remember that electron withdrawing things, or things with high electronegativity, are able to pull electron density away from the hydrogens.
Oh.
And so this hydrogen has the chlorine there that's pulling really hard, but as a second order effect, it also has the carbonyl that's pulling. So I expect that it's gonna be shifted more than 3.5 to 4.4. And so I'm not surprised that I find it not much more than that. I mean, it's at 4.4. It's just my expectation is that it would be a little bit bigger, or at least on the high side of that. Yes?
Just because they're closer together, I guess.
you wanna try something while I'm trying to do 19, it's different, because this isn't working for you. You can try to sketch the NMR of those two molecules. Imagine how you think it might look. I get 19 going, but if you want to think about this problem, like which way the ester faces, I think that's the right example. Yes? It's gonna take me a second to get 19 up. I don't know what 19 is. Okay, I did that one better. So I divided each of these by their atomic mass. I divided through by the smallest one. I got the smallest whole number ratio. My empirical formula for this was C2H4O. The mass of the parent peak is 88. My empirical formula has a mass of 24 and 16 is 44. So I'm going to tell you that my molecule is C4H8O2. Well, it looks like we might be doing ethyl ethanoate or methylpropanoate suddenly. Maybe you don't need to think about that by yourself. 88 take away 29 gets me to 59. 29 is going to be either a CHO or an ethyl. 88 take away 57 is 31. That's going to be loss of a CH3O. So if I had to write what I think I found, this peak I'm going to associate with a C3H5O plus, and this peak I'm going to associate with either a C3H7O plus or a C2H3O2.
I just only need it for these so you can tell me it's like an ester or not. Because I can't like just look at it and know.
I mean, my guess is ester. I haven't looked at the IR yet.
Yeah, but like,
You have, right? Okay. Is this going to be one of those two molecules?
huh?
Is it going to be methylpropanoate or ethyl ethanoate?
There's ethyl.
Okay, so this is perfect. So we're going to have to decide which way the ether oxygen points to. I think we're good. I think we're sitting pretty. So we figured out that our molecule is C4H8O2. Audrey's figured out the answer. She was working on it. We could lose either 29 or 31, and those fragments are both in the data booklet. So. The IR tells me that it's an ester. Probably it has a C double bond O and it doesn't have an OH. And then the NMR shows me that I have 3 hydrogens that are not split, 3 hydrogens that are split into a triplet, and 2 hydrogens that are split into a quartet. And so this is exactly the system I was dreaming about a minute ago. one of these two molecules. If I wanted to do this better, I would redraw this one, so I'm just gonna redraw it. It's gonna be the same molecule. So up here we have ethyl ethanoate, down here we have methyl propanoate. Again, this is like the textbook example of what was hard in the last problem for me. And I hope that you see that there are 3 types of hydrogen in both of these molecules. And I hope that you see that this should be split as a triplet, this should be split as a quartet, this should be a singlet, this should be a singlet, this should be a quartet, this should be a triplet. So it's exactly what I see in that spectrum. I'm gonna have to either use the mass spectrum data to see that's a really compelling looking CH3O. Say maybe that could be it. Or I could try to look at the placement in the NMR to try to decide how the chemical shift would reveal this. So the quartet has a shift of about 2. So the quartet, in both cases, is gonna be that group right there. Which one would have a shift of 2? The one next to the carbonyl or the one next to the ether side of the ester? Has to be the carbonyl side, because that's gonna have a shift around 2.2 to 2.7. It's easier when I stand over there because I can read over her shoulder. So it has to be this molecule based on the placement. We're gonna have a singlet around 4, and we're gonna have a quartet around 2. That's what we see. We can also go back in time and say, hey, you can lose a CH3O, and you can lose an ethyl. So the mass spectrum would also support this. Now this guy can lose an ethyl, but I don't see how it's gonna lose a CH3O. I don't see anything with a mass of 31 that this one's gonna give up. So there's sort of 2 ways I can discriminate between these 2 being the right selection. One way is saying this quartet appears at 2, the carbonyl has to be on this side. And the other one is saying, how the heck do I make a 31? I'm relatively sure that's gonna be methyl propanoate. If you wanted to sketch this guy, the singlet would be here in the 2s, and the quartet would be here in the 4s. So the splitting patterns would be the same, it's just the location of those 2 peaks would swap. This is the only place where I know that chemical shifts is definitively important with esters.
Wait, I understand, I just have one.
Yes, ma'am.
So you have the shift,
Yep.
2.0, 2.5, which is what I thought.
Yes, you have a O.
So we-
Yes, I just said the wrong numbers. Like I said, I usually am reading over your shoulder.
No, okay.
So I'm better
then I
at it.
understand.
Okay.
I was gonna really-
So she's mad that I said 2.2 to 2.7 instead of 2.0 to 2.5, just because my memory isn't that good and I know it should be in the 2s. I'm looking for the one that's on the carbonyl side of an ester.
Why does it swap instead of both?
So we're talking about what the hydrogens are next to, right? And here the hydrogens are next to that ether side, so I'm gonna look at the one that's 4th from the bottom. To try to identify where in chemical shift I can find it. But these 3 are next to the carbonyl, so I'm gonna look at the one that's 4th from the top. So these 3 are gonna be governed by that top rule. But down here, they're switching which rule they're following. Now I have the hydrogens on the carbonyl side versus the hydrogens on the ether side. If anyone wants to answer that question better, feel free to help me out.
Those 4 lines you put on the, near that singlet, on the graph.
Yes.
Oh, it's just that.
I said if we had the other molecule, what would happen is the quartet would be down at 4 and the singlet would be up at 2 point something.
If it was the.
If it were
it
this
was that-
molecule,
Yeah.
the difference would be that those 2 peaks would switch positions. That's why, so chemical shift matters a lot here, whereas in a lot of the things we have looked at, it doesn't matter.
Oh. Yeah. You shifted it.
Okay. That seemed like a happier yeah than.
Yeah, cause like I couldn't find it. So.
Okay, fish from the bottom.
How am I supposed to couple this?
So there are some tricks. The biggest trick is probably whenever you see a triplet and a quartet, especially after you've seen in the mass spectrum that you have a 29, your head is gonna jump to ethyl. So I don't care if this is my ethyl or this is my ethyl, I'm expecting to have a piece of this molecule that's C2H5. And I need that C2H5 piece to have a methyl somewhere else, because I need a methyl group that's by itself in this world. So in this molecule, if I had to construct it from this picture, I'm gonna draw myself an ethyl, again, quartet and a triplet next to each other, and I'm gonna draw myself a methyl, singlet by itself, and I gotta put something in between them that prevents splitting. And what I have left in this molecule is the coup, and so I'm just deciding which way that coup should face. Y'all are kind of a wreck today. Karthika didn't sleep, she looks very cold. It just. Kind of a wreck. I was hoping to learn something new, because, you know, I'm kind of tired of this. I mean, you're never gonna say learn something new.
And then you're gonna.
There's still a curriculum.
Yeah.
Sooner or later, we gotta keep learning.
Go back to the beginning work it.
You will not be prepared
Well,
for
the
the
thing is,
exam.
like, I'd like to continue to do one of these.
You don't want that.
I don't even know anthem.
So I'm not done with this. I will have a practice problem for you to test yourself with that is not one of these 20 next class. I'll probably tell you to put everything away but a data booklet, but I won't take it as a mean grade. Is that acceptable? So it'll be a test yourself moment, but it won't be like it's going in the grade book, because God knows that's the end of your happiness.
Yeah.
So I'm not asking you to study per se, I'm just asking you to maybe try one of these on your own. I didn't give you a homework assignment today. See? More winning.
And what was that coup thing? Why did you write the coup? Oh, why was that there?
I mean, Amarachi is flat asleep, we're trying to be. Amarachi looks like death has warmed over. Sorry.
Oh.
What? Like, do you remember the day that Raimi slept through class and we all let her be? Because it was clear she needed it? That's how I feel about Amarachi today. I don't feel mad at that. I feel like that poor girl needs to sleep, like she's not good.
Right.
Not all the time.
I mean, you have a back.
Case by case basis.
Yes,
Yeah,
you can
those
tell.
videos
Like,
actually help.
Feel like this was like.
Yeah. I'm, because if
I'm
Carl
sorry
walks
you're
in, he's gonna
tired.
write up in the notes, Amarachi was sleeping, why didn't you wake her up?
Because what is her job?
Because I care about her health and well-being more than I care about NMR is the answer, right?
Well, the answer.
I still haven't forgiven her for last
Because what is her job?
I wanna go back to chapter 2, that's why I'm in such a hurry to do this. Because, like, I know that you have a midterm coming up and I need some opportunities to review some old stuff.
Yeah, let's review. When is review? Let's go back.
Not today.
Go back. Oh, it's so funny. Just looking at this.
What? December 12th through 15? You don't have to go on senior trips if you don't want. So I probably made your lives kind of hellish with atomic orbitals. I tried to explain that we have different shells that electrons live in. So there's like the 1, the 2, the 3, the 4. And then within those shells, we have subshells. And we refer to those shells, those subshells, as the S, the P, the D, and the F. And within those subshells, we have orbitals.
Oh, yeah.
Every orbital holds 2 electrons. And so if I had to draw you an S sublevel, I would draw a single line. I might throw a 1s under there. I could put 2 electrons in it. But if I wanted to draw it as a 3-dimensional shape, I would draw it as a sphere. S is for sphere.
And then the P is for peanut. Peanut.
P is for peanuts.
P is for dumbbell.
Yeah, just like that.
And the D is for double dumbbell.
P is for peepers.
What I've drawn here is the singular s orbital. Each shell has 1 s orbital, and they always look spherical. The size will change of the shell. It'll go up with the radius changing as the shell number squared. So a 3s orbital is about 9 times bigger than a 1s orbital in a perfect world.
What about F?
F is flower sometimes.
F is
They're kind of hard to draw. We don't talk about those atoms, those elements.
Where would F be on
F is from lanthanum to lutetium, from actinium to lawrencium, or at the bottom. Whichever answer is nicer.
Where does that diagonal?
I'm trying to get you to transition metal chemistry. We're going to focus on the d orbital, something we've typically not talked about. So I'm going to zoom in on them d orbitals in just a second. You can call this transition metal chemistry. You can call this topic 13.
Wait, this is currently topic 2, right?
So the orbitals are from topic 2. We are then going to move in to topic 3 HL. Audrey said we're supposed to learn this a long time ago. I don't think that this has a lot to do with topic 3 SL, which is periodicity, atomic size, ionization energy, and stuff. So I skip it. I try to mix the rigor. Okay, I notice I have 3 lines here in the 2p subshell. What does that correspond to?
Orbital?
The 3 different p orbitals. So if this is the px, what would the 2 other orbitals be?
This way, and then this
Yes,
way.
excellent. You're doing great. So the D's actually have 5. And so, oh, I feel like my whole world is a better place now, don't you? Whew. Everyone cool with that? So I'm trying to show that Z coming out of the plane of the board. So you see the top of one lobe and like a little side view of that back lobe. So there's a node that is this piece of whiteboard that's bisecting the top node from the bottom node, just as my hand right now is bisecting the top node or the left node from the right node. They all have the same shape. They have some in the middle school. I've never thought that they were worth the money. Do you think they're worth the money? So the d orbitals, 5 of them have more complicated shapes. Instead of having one plane where there's nothing, they have 2 planes where there's nothing. Is that an okay statement?
Planes of nothing?
So this is a region of space where the electron cannot be. This whole plane coming out of the board. It can be above this plane, it can be below the plane, but nothing can be there. Here, it's this plane. Here, it's the plane of the board. An s orbital has no planar nodes, a p orbital has 1, and a d orbital has 2, an f orbital has 3, a g orbital has 4. Yes, there are.
Do we need to know?
No, we don't. We can though, Sophia. I know how much you want to.
Oh, yeah. You see it in my face.
So when you say a d orbital looks like a double dumbbell, traditionally this is the clover leaf. That's how I learned the word that you're expecting. And so based on how I called the p orbitals, I've just drawn you the dxy orbital. But since there are 5, I must have some more art to do. The DXZ orbital is the same shape, but it's coming out this way. It's in that XZ plane. And the DYZ is this way. All the same shape, but just oriented in different planes. The XY plane, the XZ plane, and the YZ plane.
But why is it like this? Like, why is there like just X, Y,
XY or XY. So with the P, there's only one direction that it's going, right? But in the D orbital, you have 2 directions that it's going. It's moving in the X direction and the Y
It
direction.
does come out.
Does that make sense?
All of them look like a clover leaf.
I didn't know.
So all of them look like my hand. My hand can face this
I
way,
don't think I do.
in this plane. My hand can face this way, or my hand can face this way. But each of them are that clover
But
leaf
they-
shape.
Yeah.
What they're designating is the actual plane.
That is not what you
just the
designated
axis.
Easton Morgan.
Like this?
That's not quite what it means.
If you think about it, XZ.
So it's rotated 45 degrees from there.
Got it.
Okay, so for Audrey and maybe only Audrey. That would be, like, in 3 space, do you agree that you have like, that would be a PZ. In 3-dimensional space, have you done spherical polar coordinates in your goofy math class? Spherical polar coordinates. So, like, you guys all know that X and Y can be written as, if this is theta, this is opposite, that's Y. R cos theta and R sine theta. Right? We've done that. Arga Karthika and I have totally done that. I mean, you guys are my only target audience here. Have you done this in 3 dimensions?
Is that even possible?
Yeah. So if you do this in a 3rd dimension, in addition to this, you have another angle. And when you want to write down the formula of a px orbital, you take something that looks like e to the minus r, so exponential decay, times, if it's px, this function. And that is the formula for a px orbital. And if you want a dxy orbital, you're going to divide this by more so that it's like a bigger orbital, but then you're going to multiply by both x and y. So it's going to be r squared, cosines, whatever. But you're actually like telling someone how to write down the mathematical function that we are describing. You guys did this. You are liars. AIHL, that shitastic problem that you did for the hurricane for MIT Day last year. It's an end of the problem, it's the end of the chapter exploration where you were trying to find the latitude and the longitude and the place in space. That was awful. Terrible plan. Okay, so I don't like totally disagree with him, but like I'm actually telling you how to construct a function. So that's why they have these goofy things. I chose how to construct the function by making sure it was real. So it is real, they are orthogonal to each other, and they are normalized. Orthogonal means that the integral of the product is equal to 0.
Let's talk about
But back to things you actually care about. There are 2 kind of goofier d orbitals. One of them is the dx squared minus y squared. In a lot of ways, you take the dxy and you rotate it by 45 degrees.
Do we need to know the dx squared minus y squared, or is that just like a
I'm gonna say yes, Sophia. I'm gonna go with yes. I'm gonna go with I'm teaching this because you need to know it. Like I erased all of the spherical polar coordinates that I thought my like Mohab was gonna be like, heck yeah, I learned that. And I know you two did it, and I know it was miserable. The dz squared is kind of hard to draw the way I chose the z-axis. So I'm gonna like bend my z-axis just to really kind of freak Emma out. That's my z-axis. So instead of coming directly out of the board this time, I just kind of angled it off to the side. It looks a bit like a p orbital with a donut around it. What is true here is that the cosine squared of an angle is equal to 1. There are two angles that meet that in degrees. It's around 53.8 degrees. It's called the magic spinning angle in NMR. Like it's a real thing, but there's like an angular node here. It's not quite a plane. It doesn't quite follow the rules because chemistry is really hard. This is a p orbital. P orbital can face this way or whatever. And around it is a donut.
And that's the big.
That is the dz squared orbital. It is a p orbital with a donut around it.
So what is the donut?
So the donut's actually in the xy, and the p, so it's a pz orbital. So it's this orbital. And the reason I couldn't draw it like this is because I didn't know how to show you the donut around it. I can do that if you want. I just am not sure that that's a more compelling picture.
In your mind, you just turn it big.
It's not working.
So then why is it a donut
That's-
shape?
that's the
and
problem.
not like in between two circles?
Because I call these planar nodes, but they're actually angular nodes. There just has to be some value of an angle that makes them, 0. And so you can imagine that this is some angle, right? 90 degrees, pi over 2, whatever it is. Or this is some angle at 0 degrees. This is also some angle, again, it's around 53.8 degrees, as I recall. It's wherever the cosine squared of theta is equal to 1. It's not interesting, is really my fundamental answer. We still call it a planar node, but it's not really quite a plane anymore. It's like a cone-shaped node. Yeah, I know. Welcome to chemistry. What's interesting about these and why Sophia needs to know them is because we can split them clearly into two classes. The class on the bottom, where do the lobes go with respect to the x, y, and or z axes? Through. This one goes directly on z. This one goes directly on x and y. And how about up here for these guys? Between. So I've got 3 tweeners and 2 direct. I'm going to split these into 2 sets of orbitals. Because we hate you, we will call the tweeners the T2Gs. Yeah, that's right. It's in your textbook. It's almost like you need to know that notation, but it's also like you kind of don't. And we will call these 2 orbitals EGs. G is a German word meaning gerade.
Yeah. Right along.
E means 2 and T means 3, and the 2 means something else. I promise you don't need to know, Sophia. So why are there 2 sets? Why are there 2s and 3s?
2 and 3 squared.
So I split these orbitals into 2 sets. I have the 3s and the 2. They're 5d orbitals. I split them into 2 sets and I gave them names. The set of 3 I called the T's, and the set of 2 I called the E's. And I'm just asking why.
Together, right?
You also guess why? Because the one is don't have any squares. Is that why?
No, that would be very superficially why. Something about maybe the structure.
So everyone is saying that 3 of the orbitals avoid the axes and 3 of the orbitals go directly through the axes is winning.
Wait, so, and what does that, does that give them like special
want you to understand why there are two groups. So whether Amy remembers those are T's and E's, again, it's kind of implied that you're supposed to know, but I've never seen a question about it, so I'm gonna give you the name and not worry about it. They're T's and E's. But what I want to do is I want to make those two groups different. And the way that I make them different is I come up with a compound. And the compound that I have in mind right now is the pretty blue. Yeah. That you associate with copper.
Copper's not. It is a compound that is blue, has copper in it.
Glycerine. Copper is not. What do you mean copper is not? That was actually copper's orange. Copper's a copper color.
Yes.
Copper's orange and it's green. Think of glycerine blue in my mouth. Thinking of iron man.
That's a new color. Listerine is amber.
Brown? Why would you put that in your mouth?
It was not a bit brown.
Because the color is what cleans your mouth.
Yeah, the color is what cleans.
The color is what cleans your mouth.
So I found copper sulfate. Did you guys ever, we've like anhydrous this and made it white?
No, it didn't work.
Works for me. Looks a little like Windex, tastes a little like blue Gatorade.
Really?
Is there any taste property?
Never tasted it, Mona.
That can be your
Can I smell it?
Has never smelled. I don't know what was this is leftover powder from an experiment a colleague did, so I just mixed it with some distilled water.
Just now?
Just now, I just made that solution for you. Yeah. Okay, so the compound that you're seeing there is actually this complex ion. This one, not any other one but this one. If Audrey had to name it, she might become an AP student. She would call this hexa aqua copper 2. But as an IB student, she doesn't need to name anything. This is just going to be written down, but every now and then I need to call it something. So in a terrible world, I might call it hexa aqua copper 2, but I'm just going to try to write it. Hexa 6 aqua water copper in the charge 2. And so if you put 6 things around a copper, can you remind me of the shape? From Vesper theory, chapter 14.1. It is not square, it is not trigonal pyramid. Square by pyramid, we call that an octahedron where I come from. I ain't sure that that's right-handed. I ain't sure I have enough physicists in this room to be too bothered by that.
I don't think I would care.
So the dots represent what exactly? The dots represent the oxygen atoms in water or the water molecules that are coming toward that copper center. That copper is a copper ion, it's copper 2+. There is some counter ion in that solution, some sulfate or nitrate swimming around. It's just not doing anything right now. If you were a copper 2+ and you had a water molecule swimming up to you, which side of the water molecule would you be most interested in? Do you like the negative part or the oxygen part or the part with lone pairs? You might have recently learned that water is a great nucleophile. It's not a great nucleophile, it's a nucleophile because it has a lone pair of electrons. It does some of the same chemistry here. It actually donates both of those electrons to make a coordinate covalent bond. Both electrons are coming from the oxygen to make a bond. But copper itself has electrons. what is the electron configuration of copper? And then what is the electron configuration of copper 2? Oh, back in chapter 2, everybody.
I think that's a question about isn't it, because the transition metals all have like super weird, isn't it like
There's copper and oh, because it has 9, but then you give one to the 4s2. There's copper.
There you go.
It's all no chromium.
Yeah, chromium.
You guys remember that copper is an exception, that's why I wasn't gonna use copper, but I was pretty sure I could grab some copper. But now I wanna take 2 electrons away.
4s.
I'm gonna take the 4s in one of these 3ds, and I'm gonna have, argon, because I'm bored, 3d9. So far, so good? Now, the bonding that's occurring doesn't affect this. Because the bonding is being made out of electrons that are in my ligand. The ligand is something that's about to tie to you, like a ligature mark in music is a tie mark in music. Like someone in doctoring needs to tell me what ligate, ligaments,
It comes from the
ligase. Like I didn't invent this word.
Ligate.
Oh, it makes 2 things stick together.
It's an enzyme.
Okay, so like I'm not making things up, we call that a ligand because it's going to tie in. These 3d9 are non-bonding valence electrons. Now Amarachi is a valence electron on copper. She's just happily going about her business. She's in one of those 5 orbitals we carefully drew out. And water is coming in. Water's a bit of a bully. Karthika mentioned it had a negative side. How is Amarachi going to feel about these negative things coming near her?
Repulsed.
She's going to feel repulsed. That is right. It is going to raise her energy. But Amarachi had a decision to make. Amarachi could either be in an orbital that looks like this, or an orbital that looks like this. That is, she can be avoiding the x, y, and z axes, or she can be along the x, y, and z axes. In which case would Amarachi be more upset that the waters are coming in? Along, right? The water's right here. She's going to be extra mad. So we can actually draw an enthalpy level diagram just for you.
Water, never mind.
Where we have these d orbitals by themselves, and then we came along and we added the waters, and that made them all mad. But as the waters chose to make this octahedral compound, what we will find is that the orbitals are split into 2 levels.
She's taking the d orbital of the copper. She's splitting it into the 2 different types of orbitals to show you, hey, this is where the
So there are
bonding
2
might
levels
occur.
of this. The first one was, uh-oh, a bunch of negative stuff is coming. Sophia told me they would be repulsed. So I showed that as the energy going up. But then you guys were able to discriminate that Amarachi had 2 choices. She could either be directly impacted by the water coming in along the axis where she is localized, or less impacted because she is avoiding the water by being in between the axes. We will find the 3 on top, the T2Gs, they're on top over there, are slightly lower in energy, but the 2 on the bottom are higher in energy. This distance is called the crystal field splitting energy.
CFSE.
There are 9 electrons here. When you shine white light on this compound, it is actually able to absorb 1 color. It absorbs orange light that is directly resonant with this crystal field splitting energy. What you are seeing right there is 1 electron moving from here to here. That corresponds to visible light. What is special about transition metal compounds is they make pretty colors. That's why they get their own special region of your chemistry book. They're pretty.
And this same concept applies to like other transition metals, so like.
Yes, it
they'll-
does.
So they'll also be like repulsed, there won't ever be a case where like.
They are always repulsed.
Okay.
And we are gonna learn, next time, why, oh, I don't want it white, I want it blue. Or, that's an AP problem right there, let's keep adding, so we pretend that we're not AP students. Why did this change colors? Why is it now cerulean blue
So.
and a little bit milky?
You going from
It needs more. Why did I change the color? What has happened there?
like.
I made this bigger or smaller. I am able to change that by changing this ligand from water to ammonia. I put very strong ammonia solution in there. Ammonia makes a better bond to copper. It gets in closer, it pisses Amarachi off more. Bigger splitting, prettier color.
So every time you go from K2G to EG, you're gonna have a different color because it's light absorption. And
You're
that's
gonna be
adding
able-
electrons into a different